Okay, so Unit 5 covered work and energy, which actually I tend to like this unit because I feel like it's one of the easier ones. You don't get all the crazy trig in it and everything like that. So it's a little bit simpler in my opinion. Okay, so we want to look at work done by constant force, the kinetic energy and work energy principle, potential energy, conservative and non-conservative forces, mechanical energy, the conservation of mechanical energy, and then problem solving using conservation of mechanical energy. There are other forms of energy and how that changes things with the law of conservation of energy, and then looking at dissipative forces when you're solving problems. Also power. So we've only looked at motion in terms of forces, and now we're going to look at it in terms of work and energy. So this can be really nice because you can then look at things in terms of work and energy, or you can look at it for projectile motion. And so sometimes doing the energy problem makes it easier. Now, there's a very precise definition in physics when we talk about work, and we're looking at what is accomplished by force in moving an object through a distance. Okay? So when you have a constant force, you have work being done, and you multiply the distance by the component of force that's in the same direction as the displacement. Now, I hesitate with the distance word, though, because it depends whether you're looking at distance or displacement based on whether you have a conservative or non-conservative force. So just keep that in the back of your mind when we get there. But for right now, we'll say that work is equal to force times distance times the cosine of the angle between the two. So that way you're getting that component of the force that is in the same direction as the displacement or distance. Okay? If your force and displacement or distance are parallel, then work is just force times distance. Okay, and this is a really simple example here where you apply a force of 30 newtons over a distance of 50 meters in the same direction. So you do 1,500 newton meters of work, but a newton meter is actually something we combine into a joule. So you'll see also that energy has the same units. So work and energy have the same units, which are joules. Now, something that a lot of people struggle with here is if your force and distance or displacement are at 90-degree angles to each other, no work is done. So the example here of this guy carrying a bag of groceries, he is applying a force upward to counteract the force of gravity, but he walks the groceries sideways. There's no work done. And people are like, well, there has to be a force put on these groceries because they're moving. Well, no, once you get them in motion, they'll stay in motion. And so you don't have a net force in that direction. So when we're going to solve these problems, some steps to take. First is to draw a free body diagram. So you still have to look at the forces. You still have to draw a free body diagram. So we brought free body diagrams in Unit 4. They're here forever. Choose a coordinate system. Apply Newton's laws so that you can find any unknown forces. And then we want to look at the work done by a specific force. Or we can look at the network. So if you're looking at the network, you can either find the work done by each individual force and sum them, or you can find the net force and then put that into the work equation. Either way, you'll end up with the same answer. Okay? So if we look at this example here, we have gravity acting downward, we have the normal force acting upward, we have a pull force acting at an angle, and a frictional force acting opposite of the direction of motion, and we displace the box 40 meters. So in terms of the work, we would have to consider the net force in the x direction. So we would want the horizontal component of the pulling force and friction. So we look here, and if we have a force of 100 newtons pulling, we would take that component to find the x direction, that part that does the work, and we have to subtract the frictional force from it to find the net work that is done. And you can see that down below. Okay? here we have a hiker going up an incline. Now, gravity points straight down. The hiker is moving upward against gravity, and then our displacement's at an angle. We only want the component of force that's in the same direction as the displacement for the net work that is done. Okay? Now, since we have the work that the hiker does as mgh, and the work that gravity does is negative mgh, the two cancel out. So there's no net work done on the backpack. Okay? There is work done. The hiker does work on the backpack. Gravity also does work on the backpack. So there's work, but the net work total on the backpack is 0 because one cancels out the other. Okay? And this jumps a little bit back to our circular motion and also into our head into our planetary motion. But this, let's look at this a second. Okay? If we have, let's say the moon does have a perfectly circular orbit. Okay? We know it's a little elliptical, but let's say it's circular. Okay? Now, the work done, or the force that exists between the moon and the earth, is the force due to gravity, and it's always pointing towards the center of the circle. Okay? And the direction of motion is always at a 90-degree angle to that force. Because they're at 90 degrees, that displacement's also at 90 degrees. Therefore, centripetal forces don't do any work. Okay? When you have circular motion, centripetal forces do not do any work. Okay? Because they're always perpendicular to the direction of motion. Okay? Now, energy was always defined traditionally as the ability to do work, and then work is the force time is the change in energy. So it was kind of this cyclical definition, but that's okay. Okay, so we're looking at mechanical energy. Okay, energy is the ability to do work, and then we look at kinetic energy. And energy is the energy of motion. Kinetic energy is the energy of motion. Okay? So that means an object in motion has the ability to do work. Okay? If we want to equate those two. Okay? So if we look at a bus that's moving along and it has some velocity, v1, and a net force is applied to it, we know that means acceleration. Therefore, there's going to be a new velocity later. Okay? Some distance later, d, there's a new velocity, v2. Okay? So now we've had an acceleration. That's how we've been looking at it before. Now we can look at it in terms of the work that was done on the bus, because we know a net force and we know the distance over which the force was applied. Okay? So if we look at Newton's second law, F equals ma, and we also go back and look at our kinematic equations, okay, that our v2 squared equals our v1 squared plus a times d, right? And we solve for a. We also know that the net work done is equal to the net force times the distance. So now we're going to combine all those equations, right? Because F equals ma, and we're going to substitute in ma for our net force in the work equation. But then we have where we can substitute in the acceleration from our kinematics equation. And ultimately what we find is that work, the net work done, is equal to the change in kinetic energy. So when the kinetic energy of a system changes, work is done. Okay? Work is done. And so we can equate the two. Okay? So we're looking at translational kinetic energy here. You can have positive work, you can have negative work. If you're increasing your kinetic energy, you're putting energy into the system. Think about putting money into a checking account. You'd put that in your ledger as a positive. And if you're decreasing your funds, you'd say negative. So negative work means the kinetic energy is going to decrease. Okay? Work is a scalar, though. It doesn't have any direction. It can be positive and negative, but it doesn't have any direction, so it is a scalar, okay? And joules are a unit for work. They're also a unit for kinetic energy, okay? Let's look at a hammer on a nail system, okay? So here you've got the hammer, right, is moving and comes to a stop when it hits the nail. Then you have the nail is not moving and starts moving after the hammer hits it, okay? So if we look at the work that is done on the hammer, initially it was moving, it then came to a stop. So its final kinetic energy is 0. It has some initial kinetic energy. Therefore, it decreased its kinetic energy. So the work done on the hammer is going to be negative. The nail was 0 and then started moving. It has positive work. Okay, the energy that was lost by the hammer is going to be gained by the nail. Okay, now they're going to have different final velocities because their masses are different. Okay, but ultimately the energy lost by the hammer is going to be gained by the nail. Okay, you can also have potential energy. So kinetic energy is the energy of motion. Potential energy is energy due to position or by its surrounding, its virtue of its surroundings. So you can have elastic potential energy, and that's where you've got a spring that's compressed or wound up. You've got an elastic band that's stretched, right? We've done lots of rubber bands with things and they bounce. You can have something that's just sitting at a height above the ground. It has the potential to fall, to move, to increase its motion because its gravity can do work on it. Okay, if we look at raising a mass, okay, I'm holding something, I'm going to put an external force on it, and I'm going to give it more potential energy because I'm going to increase its height. Okay, we then find that there's work done, and therefore we can look at gravitational potential energy, and that's mgh, or the change in position. Okay, and we find that the work done by gravity is equal to the negative change in potential energy. Because gravity is trying to go this way, I'm going that way, therefore they're opposite. Okay? So the work done by an external force to move the object of mass m from point 1 to point 2 without acceleration is equal to the change in potential energy between positions 1 and 2. Now, if I have potential energy and I drop this, okay, I will change my potential energy to kinetic energy. Okay, it's very simple. It's a straight change. Okay, however much potential energy this loses, it will gain in kinetic energy. Okay, so it's just straight trade. All right, if you have a compressed spring, okay, and I compress it, okay, this elastic potential energy will change to kinetic energy. And again, it's a straight trade. Okay? If you remember, we find the force, okay, that a spring exerts based on Hooke's law, which is negative kx. That's the restorative force. Okay, k being the spring constant, or the spring, the spring constant. It's measured in newtons per meter. Okay, we can then find the work done, okay, by the spring or by me, the external force, and we find that elastic potential energy is then 1/2 kx squared when we look at the work that is done, because we can look at the area under the curve of a force versus displacement graph, which is going to be your work. So that also leads us to, if we're looking at the area under the curve, we're looking at an integral. So work then is the integral of force dot dx. Or, yeah, force dx. Okay? All right, let's talk about conservative versus non-conservative forces. When you have a conservative force, it doesn't matter what path you take, the work is going to be the same. So the work done by gravity, if this thing falls this way through the air, or a piece of paper is more likely to float this way, okay, Gravity's going to do the same amount of work no matter what the path. Excuse me. However, a non-conservative force, it does matter the path. So this is where we get into the distance versus displacement, okay? If I just drop something, gravity only acts in this direction, okay? It doesn't matter with a path. That's a conservative force. But if I have friction, okay, the longer my path is, the more energy I'm going to lose due to friction, okay? So that path does matter. So that's where you want to use distance instead of displacement, okay? And we can see this here. If we were to take the lower path, right, we're going to have less distance over which friction is acting. So there's less energy loss to the system, okay? Whereas when you look at the second path, the upper path in the picture, this distance does matter, and so we have to take that into account, okay? So here's examples of conservative forces and non-conservative forces. We don't deal with electric forces in this class, so you don't have to worry about that. So gravitational and elastic are the only conservative forces you have to worry about here. Friction, air resistance, tension, rocket propulsion or a motor propulsion, and a push or pull by a person. Those are all non-conservative forces. So that's where the path matters, so you have to do distance. Okay? So we then need to look at how this affects our energies. Okay? When you have a non-conservative force, you're going to see the total energy of the system change. Okay? And I'm going to show you energy diagrams after this, and I'll show you how to take those into account really easily. It's a really nice little trick. Okay? So when you have a non-conservative force, there's going to be some gain or loss of energy because there's going to be work that is done on the system. Okay, either a positive work or a negative work. And the work that's done is going to equal the change in the total energy of the system. So either the kinetic or the potential or some combination. Okay? If you don't have any non-conservative forces, so you're in a frictionless system or air resistance is negligible, something like that, then your energies are going to be constant. So your total initial energy is going to equal your total final energy. So here for this marker, I'm dropping it over such a small distance. Air resistance isn't a factor. There's no friction. I don't have any tension. I'm not pushing or pulling. The only thing acting here is gravity. So right here, all potential energy. As this falls, that potential energy is being converted to kinetic energy. If I add my total energies here, 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 all the way at the bottom, it doesn't matter. It's always going to be the same. Okay? So that's what this slide is showing. Instead of a marker, it's a rock. At the top, you've got all potential energy. About halfway down, you've got half kinetic energy, half potential energy, and at the very bottom, before the rock stops, it's all kinetic energy. Okay? And this is where instead of using free fall, sometimes it's really nice to use energy. So here they're talking about energy buckets. I'm going to show you an energy diagram here in a little bit, and that might be a nice little trick to use. Often when I teach this, people will be like, oh, you learned energy from a high school teacher. Yeah, but it works, so what does it matter? Now, this is kind of a nice little thing. If you're riding a roller coaster, okay, if you have a frictionless roller coaster, the highest you'll ever be able to go is the height of the first hill, okay? So when you have a roller coaster and that chain pulls you up, okay, you're putting energy into the system because the chain is doing work and it's bringing the roller coaster up to some potential energy. Now, if there's no chain anywhere else in the entire path of the roller coaster, that hill has to be the biggest hill, okay? Because we do have friction coming into account. So as you go through, you're going to be losing energy. So you will never be able to regain all of the initial potential energy. If there is no friction, then you can regain that initial height, but you'll never be able to go any higher unless there's a second chain to do more work. Okay? elastic force. You can also have an elastic force that puts energy into the system. Let me see if I can get a popper that sticks. I got a couple polar bear poppers here, but if I take my little polar bear popper and I push him down below here and then I let him go, woo! You see that the elastic potential energy becomes kinetic energy, and then as this thing goes up, 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 that kinetic energy is becoming potential energy till it reaches its peak. All potential energy starts coming back down, potential energy becoming kinetic energy, dot, dot, dot. Okay? Other forms of energy, electrical, nuclear, thermal, chemical, we don't do these in this class, but be aware, especially because when you have friction, typically you're losing mechanical energy, but that energy is becoming thermal energy, so the total energy in the universe is still conserved. Okay? And that's what I just said. Okay, so in general, we know that when you have a non-conservative force, you've got work, and so there's going to be either a gain or a loss of energy to the system. Okay, so we have to watch that. And when it's friction, it's going to be a loss to the system. So we can take all that into account. Okay, tips for solving problems when it comes to energy. Draw a relevant picture. Determine the system for which the energy will be conserved. So is it just this object, or is it two objects together? And what's your y equals 0 value? So where's the potential energy equal to 0? Okay, choose a logical frame of reference. Don't choose something weird and make the problem harder than it has to be. Okay, apply conservation of energy and then solve. Okay, power is the rate at which work is done. Okay, so here we have work over time for average power. If you want instantaneous, you're taking the derivative, dW dt. Okay, the units for power is a watt. It's a joule per second. Yes, the British units is horsepower, and so you hear that all the time when you're talking about cars in America and all that sort of thing, but we're scientists, we're not going to use that. Okay? So if you were to walk up the stairs, you're going to do some work. Okay? You're going to work against gravity. All right? Now, what's the difference if I walk up the stairs versus run up the stairs? Well, the difference is power, because the rate at which I'm doing work changes. I do the same amount of work no matter how quickly I climb the stairs, but my power is different. Okay? Since we look at average power being work divided by time, and work is force times distance, we see the d over t, which is average velocity. So your power can also be found by taking the force times the average velocity. Okay, so here we've got an example of a car on an incline. Okay, for part A, we're going to have a constant speed, so our acceleration is going to be 0, so that means the sum of our forces in the x direction is equal to 0. So when we take the parallel component of gravity and friction, that's going to be equal and opposite to the force that the car is applying to go up the hill. Okay? And so we can then look at the velocity. Now here they're using horsepower, after I just said we're not going to use it, but they did. So we found our net force, and if you know the velocity of the car, you can then find the power. Okay? Let's say we do have acceleration now. Okay? So now we've set theta equal to 0. So now it's just going to be our car's force and our friction in the opposite direction. You can find your acceleration, and then you can find your net force, and therefore your new horsepower or new power. Okay? So just a quick summary of things, and then I want to show you some energy diagrams. So bear with me here as I switch to a new window. Okay, so energy diagrams. Okay? When you have an energy diagram, this is a really nice little useful tool. Very simple to use, okay? So for an energy diagram, what I want to draw is starting out this way. This side's going to be my initial conditions. This side's going to be my final conditions, okay? In this side, I want to list all my different types of energy, okay? My gravitational potential energy, my elastic potential energy, my kinetic potential energy. Over here, I'm going to do the same thing, okay? Now, if I have a system where I have a non-conservative force acting, so the marker falling, or actually, let's do the little bear popper, okay? Let's look at my little bear popper. So initially, I squish him, and he's sitting on my desk. We'll call my desk height equals 0. So I have all elastic potential energy here, 1/2 kx squared, okay? And then he pops, okay? And let's say I want to look at him halfway through his ride to the top, okay? At that point, he's got some gravitational potential energy and some kinetic energy, mgh, and 1/2 mv squared. Because this is a conservative force, there's no net work done on the system. So that means I can set my initial energy equal to my final energy. So I'm going to take everything from this side and set it equal to everything from this side, okay? If I know values, I can then plug in and solve for something, okay? Let's say I examine a system, okay, and let's look at the roller coaster example I said, where okay, we've had something pull the roller coaster up to the top of the first hill, and it's sitting, waiting, ready to go, okay? And then it drops. It starts moving, okay? There is friction, okay? I get to the bottom of the first hill. I'm not at ground level. Let's say I set my ground level to be equal to 0. So I've got a little potential energy here, okay? We'll call that 2. And I've got some kinetic energy here, okay? But when I add this all together, this doesn't equal that, okay? It's because there was some energy lost due to friction. There was work done. So your work is this circle here. It's the difference between the two sides, okay? So work is going to equal my frictional force times my displacement. If I want these two sides to be equal to each other, I would have to say mgh is going to be equal to mgh2 plus 1/2 mv squared plus the work that was done by friction, okay? If the final side is higher than my initial side, that means work was done on the system. Energy was put into the system. So my arrow would point the other way, and my work would be on the other side of the equation. It's just a really simple pictorial way to help you set up your problems. So hopefully that gives you an overview of work and energy, and this was helpful.